The BritChips podcast is proudly sponsored by Silicon Catalyst UK. Hello, I'm Anthony Miller and welcome to the BritChips podcast, where I have conversations with movers and shakers in the UK semiconductor startup scene. Now, my guest journey today rather mirrors the progression of the development of optical computing, from simple pattern recognition through pattern correlation and convolution, optical free-space communication, and fully homomorphic encryption in a photonic integrated circuit. And no, I cannot explain what any of that means, but my guest surely can. He's Dr. Nick New, co-founder and CEO of Leeds-based photonic computing startup Optalysys. Nick, welcome to the BritChips podcast.
Thank you very much. Pleasure to be here.
That's grand to have you. Look, Nick, before you enlighten us all on the technicalities of optical computing, let's start at the beginning of your journey, because you studied electrical and electronic engineering at Liverpool University, and then you went on to Cambridge to earn your PhD in optical pattern recognition. Why that?
So, optical pattern recognition is a really fascinating technology dating back all the way to the 1960s or so. It was a technology that promised a great deal, but was held back really by the availability of interface technologies that allowed data to be moved from the optical domain, from the electrical domain, and then vice versa. Again, at the time when I was looking for interesting things to work on during a PhD, this struck me as something that could really be brought out of the lab and commercialized, largely due to the fact that there was a key piece of technology being developed in terms of liquid crystal microdisplays at the time, which allowed very fast data rates in comparison to previous versions, but also very large resolutions of data, so increasing the bandwidth of the data that you could bring into the optics.
So you always had an eye on the commercial side of the technology, it sounds like, right from your university days.
Yeah, I always liked the idea that we could build something quite dramatic in terms of its impact or potential impact for the world, but do it in such a way that we could really make a difference. So actually taking technology out of the lab was always a key interest of mine.
So that's because that's when you started Cambridge Correlators, because you left Cambridge University, if I got it right, in 2001, and then you were one of the founders of this startup called Cambridge Correlators. I think at the time you were its CTO. What did Cambridge Correlators do?
So Cambridge Correlators was largely an R&D outfit, but with the express task of bringing this technology that I'd worked on for 3 years within the kind of dark rooms of the optics lab in Cambridge, and really start applying into different application areas. So it was really a vehicle for allowing us to develop the technology further. Now, looking back, we did it with a very shoestring budget. Took several directions in terms of where to place the technology. And it remained a kind of R&D outfit for many years, working particularly in sort of defence sector projects with prime defence contractors, for example. Quite similar to where the roots of optical processing have been for many years preceding that, but bringing this new generation of interface technologies through the liquid crystal devices that were being built for originally rear projection TVs, those of us who are old enough to remember such things, and also head-up displays or near-to-eye displays. So this is using a technology being built for those types of applications, but in a very different way. So effectively using a display as an input to the optical processing system.
We will come back to that, but were you then working with your sort of other colleagues from Cambridge University? Was it like a bunch of you started this up, or did you recruit others into the team? Or
so we recruited others as well, as we always had that very close link with the university. It's actually spawned out of the university through an industry partnership as well. So we're actually backed by a chemicals company in the northeast in County Durham to begin with that looked at commercializing or bringing out technologies from labs. So photonic switching was a big area of activity at the time. So the ability to route telecoms through free space optics and in particular liquid crystal displays was a key sort of building block and factor in the formation of the overall technology, particularly on the interface side. And this was quite different in terms of moving into the sort of pattern recognition um, side
Oh,
of.
okay. Because I was going to ask, it sounds like you were developing exciting technology to base in defence. What happened then to Cambridge Correlators that prompted you to, go on to the next, so to speak?
So we did several years of developments, particularly in defence circles. We effectively had come to a point where we were trying to move into more commercial activities. We had a lot of ideas in how to take the technology forward, and we found at the time that actually to do that would be it would beneficial to kind of move away from the defence sector as such to help spawn private investment from seed shareholders at the time, and thus was formed Optalysys from the IP that we created from Cambridge Correlators.
Okay, so in effect, you kind of split off from Cambridge Correlators and left them to do their own thing, so to speak?
Now we moved all the IP across, so the old Correlators came across as well. So we managed to do to bring the patents that we'd put together during that time, which were crucial for the early formative work in Optalysys. But because we'd got such different directions to go in, and the technology was looking very different by that point, we wanted to make that real shift really to allow us to bring in the private investment that we were talking to.
Right, right. I make it a far more commercial proposition.
Yeah,
Yeah, yeah,
exactly.
yeah. Because you co-founded Optalysys with Robert Todd as your CTO. Was Robert one of the guys you worked with at Cambridge Correlators? How did you get to know each other?
Yeah, so being from the north of England, I had lofty ambitions to really do what Silicon Valley does, but in the north of England. And we took Cambridge Correlators out of Cambridge, where we started it, moved it to Yorkshire, and began to tap into the optical expertise that actually Yorkshire is very strong at, both in terms of local companies to allow us to build technologies at reasonably low cost, and also to tap into the local universities that had very good skills and experiences and courses running photonics type modules. So involvement with Rob started back in around about 2004. And his background is actually in optical, precision optics, and actually building and creating optical components such as lenses and so on. So,
So
it was
this was his own business. He had a sort of an optical thing. Oh, wow, up in Leeds.
absolutely. It was a really interesting partnership because it allowed us to have quite a rapid cycle of developments in terms of building free space optical systems.
Okay, we'll come on not into too much more detail on that, but I'm just curious about how you met Rob, because he's running his own business making lenses and other good stuff, and you're doing your thing. What, you sort of kind of met him in a pub in Leeds, and you had to be chatting, and he said, "Oh, why don't we do it together?" I mean, how did how did the meeting of the minds happen?
Yeah, well, it was actually through the local council, I recall, that in Wakefield that actually introduced us. And the um, back then, the sourcing of optical components at relatively low costs and in very custom configurations um, ultimately decided the size and shape of the systems and the cost of the whole systems were very much dependent on the optical components. So to be able to find someone that could basically have full control over the production of those components allowed us then to customize the technology in ways that we couldn't before and actually produce this in a very cost-effective and timely manner. So that's how we came together really, and the optics business that was being run from Wakefield supplied some of the major catalogues where you would source optical components ultimately. So it was almost going to the source of those optical components by doing that. And then the partnership was formed, and obviously we still work together 20 plus years later.
Well, that was a very sort of propitious meeting then. That's great.
Absolutely, yes.
But when you and he started Optalysys, what was the dream?
Um, the dream, which has never changed really, in terms of this, we had this core technology that had huge potential attached to it in providing a huge benefit for computing. So this was always and always has been the same theme in terms of bringing this analog optical device into a digital context, as in a digital circuit that ultimately interfaces to the outside world, and the benefits that that could bring for computing. Now, that's changed a lot over the years in terms of its application. We started obviously on the optical pattern recognition side, and now the technology looks very different, as I'm sure we'll be talking about. But the core theme of this is really taking advantage of what that mathematical process was in the optical domain, but supplying it into a digital setting. So the digital circuit that ultimately encompasses the optics. What we've done over the years is really develop the means by which we can take advantage of the optical process, but keeping it within that digital setting. So, to begin with, the as we call them, the free space or classical optical approaches, i.e., the systems with the lenses, beam splitters, and other sort of associated optical components, has very much changed in terms of size and shape, in that we don't even have classical optical components within the system now. It's all in the plane of silicon, as we'll come to. But the core theme of the advantage in terms of supplying the maths that the optics is very good and efficient at doing has never changed. The application areas have changed significantly, but the overall the theme of this has never faltered.
Well, that actually is the application areas I was wondering about, because when you started all this, where did you think the technology could be used? Because it sounds like you were just trying to make, a faster chip, but it was going to be optical instead of silicon. Where did you think you would be able to apply the technology in real life?
Yes. So some of the early application areas, stretching all the way back to university days, I think one of the first areas was in urine sample inspection. Would you believe, in looking at cells through a microscope?
Okay.
Things that maybe shouldn't be there, like sort of proteins or various cells that need to be picked up on in our medical analysis. We had Formula One related applications in terms of slip angle detection, where an optical sensor under the car would be determining the angle at which the tires were pointing as compared to which way the car was actually moving at the time. But we were never far away from more defense related applications in the classical optical pattern recognition sense. The technology itself has roots in things like satellite photograph analysis. So the kind of original application attached to this was the tank in the bush. So the ability to pick out patterns from very complex scenes with this process. We were never too far away from that. Now you can also do frame-to-frame comparison, for example, or analyzing video frames, picking out changes between them. So the things like MPEG type compression, we're picking out
Yeah.
the vectors between frames and picking out similarities between that. So to begin with, in the earlier days, the types of applications are really along the lines of processing high resolution video feeds, which electronics struggled at the time. As we move forward, the types of defense related applications included bringing more and more functionality to the sort of overriding system that had the optics at the heart to it. So I mentioned data compression and the pattern recognition or target detection type applications also included things like navigation, And again, going back to that relative motion detection between frames,
Yeah.
a constant theme within that. And we also did some early work in, as I mentioned before, computational fluid dynamics, looking at how we could use the optics in terms of generating derivative functions, so rates of change,
Oh,
that
rates of
how they
change. Okay. Yep.
the
Yeah.
bedrock of large numerical models at the time. So,
Okay.
so the maths, the central maths, was the key part of this, and how we actually brought that optical function into larger systems was the current, and still is very much the theme of what we do.
Okay, well, we will talk about where you are now with the optical bit, because actually your first, but this is what confused me at first before we had our original chat. The first product you've actually got on the market, or just coming to the market, has got nothing to do with photonics at all, has it? This light locker. Can you just talk a little about that? What, how that came into the sort of Optalysys sort of development cycle, and where that will lead in terms of what sounds like your core business, which is the photonic bit.
Yeah, I guess the maybe worth going through a little bit background of how we came to FHE and secure computing as well. So when we started Optalysys, we had a large development into actually genetics and alignment of genetic data through string matching processes through correlation again. We moved after that into areas which really had a theme of a kind of maths coprocessor attached to them. So again, looking at how we could bring this in those days into a tower PC case. So we had early stage products in this, where we had the optical systems actually mounted to electronic boards, so FPGA boards, to drive the data to and from the optical process.
So you did
We had
actually have optical technology at that point.
Yes, indeed, and
Yeah.
we moved into an application area which is very familiar now in AI, where we were developing the convolution layers within convolutional neural networks,
Well, hang
which
on.
related to images.
Convolution. Can you just kind of, is there a sort of a simple explanation for that, for what that is?
Yeah, so think of how you would effectively pass one image over another image, and do a mathematical operation based on the kind of overlap with that, and then move that image across pixel by pixel. In terms of the maths behind that, that is a convolution as opposed to a correlation, which relates to the pattern recognition side. Mathematically, they are very similar operations, though. So we could effectively perform those convolution operations with the same optical system, and thus we could build up AI models. And this was back in 2014, 15 or so, that then allowed us to build up larger AI models based on convolutional neural networks, or CNNs, that was a very active development at that time. And again, it was using the strengths of the optics to perform those convolution layers, and mixing in with the electronic sort of back end layers to that, where the optics could provide an advantage for analyzing high resolution video frames in particular. The challenge for us back in those days was, well, we had some really good advantages that we could provide for very niche or specific AI models, but to apply more general or standard CNN models at the time was very challenging, because we're always stuck with this very large resolution process. And of course, within the digital setting, the models are based on very small functions. So we had a major pivot around about 2018 or so, as we considered how we could perform those standard models much more effectively with this optical process. And thus we took out the liquid crystal elements. We moved to silicon photonics, which back in those days were very much rooted in sensors and also transceivers in
Right.
terms of communications. And that allowed us to push the effective frame rates, so as we call them frame rates from liquid crystal days, which we still
Mm,
uh, call them frame rates,
yeah.
um,
It's basically like
from
like a switching speed, is it? Yeah.
exactly, yeah. So moving from the hundreds or low kilohertz up into gigahertz realm, but also bringing the resolution down, which pushed us into thinking how we could provide the benefits of the this optical process less on the resolution, so moving from the very, very high resolution functions into much smaller, lower resolutions, but pushing the speed at which we could run those operations much faster. Um, and around about that same time, we started looking at interesting areas which were heavily dependent or based upon those transform operations that the optics could produce very effectively. And one of those was in an area that was relatively new to us, which is post-quantum cryptography. So,
Post-quantum cryptography. Okay, so
oh, yes.
basically being able to, or not being able to unpick cryptographic keys.
Yeah, and that was a really interesting area to get into. So this impending threat from quantum machines in the distance that threaten to break standard cryptographic schemes that underpin our everyday lives on the internet and cloud computing to financial transactions and WhatsApp messages and so on. There was a set of methods that could be accelerated with the transform or accelerating transform functions would provide an overall benefit that could not be mapped to a quantum machine to potentially break. So that was a really interesting area of exploration for us. We implemented NTRU, which is one of the main PQC methods at the time with an optical process, and then we hit upon this set of applications under the banner of fully homomorphic encryption,
Now,
which
just explain what that means, please.
yeah, it's really interesting technology in itself, which had advanced tremendously in the early 2000s, about 2010 onwards, that allows encrypted data to be processed arbitrarily with an encrypted answer being given back. Now, what that means is that where traditional cryptographic schemes protect data whilst it's at rest or whilst it's being moved. When you have to process the data, you typically decrypt it first, and that leaves it vulnerable. Now, in today's world, protecting data, uh, as you know, is a very, very hot topic.
Sure.
The ability to keep data encrypted, so the ability to protect it under a quantum safe algorithm, move it along potentially untrusted networks to the cloud, run processing on it, so run AI models or any other type of processing on it, and produce an encrypted answer that then gets returned to source, actually opens up whole new ways of using data going forward. And this was really exciting.
So this was your
To
light bulb moment. You realized that you could apply the technologies that you were developing to being able to process encrypted data without having to decrypt it, basically, and pass it on to whatever is the next stage, still fully encrypted. No sort of no exposure then to the original data.
it was a really exciting moment, and indeed, but it's also a really good example of processes that are built on those math functions that the optics are extremely efficient at. So for us, it was a perfect example area to work on to show the strengths of the optics and provide something that actually no other company could do. Yeah, so what we have is in development right now are integrated photonic chips. In terms of the fully integrated versions, we're about 2 to 3 years away from those. As a starting point, we have the processors that we are running in a digital sense, or through software plus digital, on programmable FPGA devices, which go in our light locker server units right now, but as a precursor to having the photonic elements added in there. So, in other words, the products, the light locker products we have right now, provide the infrastructure for us to add the photonic BritChips, which are under development right now, but they also allow us to effectively seed the technology in terms of, in particular, the FHE-based workflows that we run in an advantageous manner compared to conventional chips such as CPUs or GPUs.
Okay, so it's the common architecture, if you like, but with the light locker product that is fully digital at the moment, based on FPG. Would never get that acronym right, FPGAs,
Yeah.
but it is sort of the stepping stone to a full photonic chip implementation. I mean, you're selling the light locker box now. I mean, do you have customers for it?
Yes, absolutely. Yes, we're shipping the first ones in the next few weeks.
Oh, great.
We announced that in the second half of last year. The initial versions of that are targeted towards blockchain applications. The reason for that is that there is a strong push and momentum within banking and finance to move to blockchain-based systems. So a lot of the traditional banks are now looking at blockchain to replace their financial systems that have been in place for many years now. The ability for blockchain to process transactions extremely quickly and efficiently, but also without that central uh, uh, point at which all the processing needs to be done, is a really strong attribute. Where it falls down, though, is that the nodes on which the processing is done, so all the financial transactions in this case, are all visible. So you cannot have that within mainstream finance. Now, if you replace the unencrypted data with FHE encrypted data, you can run those transactions without each node actually seeing the transactions themselves.
May I ask, are these clients in the UK? Are they overseas? Where are you seeing your initial clients from?
Yeah, some are in the UK, some are overseas as well. There's a strong push, as you've seen from the likes of the US government, for example, into stable coins, where traditional finance organizations are getting involved in this now. So it's a very active area of development. For us, it's the first of many different areas that this technology can be applied to.
Such
So
as?
so in terms of FHE, so if you think of how data is used, if you think of it in a kind of Web3 context, where you've got a multitude of sensors, the flow of data is everywhere around, a high degree of automation in smart cities, for example, then the flow of, in particular, personal and confidential data is crucial. It's effectively the blood flow of the internet going forward. If you cannot protect that, in that if there is the ability to basically steal that data and use it for nefarious purposes, then it doesn't work. So the ability to actually run those processes under encryption is actually a key theme of how we should think about the internet cloud computing going forward. The other key areas where this has been applied, so some of our strategic developments in the UK, for example, is into such things as secure database queries, where you may
Right,
wish to obscure the
right.
actual query going into data sets. You may wish to apply secure AI processes as well, where in fact the data going through the AI models can be protected from actually being used in the AI model going forward. So the ability to protect data is a central theme to this. Also, the ability to actually use data in different ways, the ability to share data without exposing the data itself is a really useful attribute of these algorithms as well, where for either commercial or legal reasons, you may wish to be working with a company, say, but you may not wish to share the data with a
Ah,
company,
okay.
provide services beyond that. So areas, and banking is a strong one in this, where fraud detection can be applied to sharing of account-based data without actually sharing the data
Without
itself.
revealing
So
the data. No, I get it. By the way, out of curiosity, where is the box actually made? This light locker thing is a box, isn't it? Where does it manufactured?
yeah, so we have partnerships with Dell, with an integrator called BSI in this country as well. And we assembled that here within Optalysys and also within our supply chain partners. We've done this in very much an enterprise grade way. So the infrastructure around the core technology itself is all there. The supply chains are set up. Um, so ultimately, it's a number of different places we source the components from. There's a range of options going forward of how we resource the various parts of the
But
technology
the ultimate
going forward.
assembly is done in the UK.
Yes, indeed.
You,
Yeah.
that makes sense. So how does this transition then to? I think you said you're still 2 or 3 years away from a fully photonic chip uh, to do this. And meanwhile, of course, I assume you're going to be selling Light Locker, Light Fury, because that's going to generate revenue for you and help with the funding, which we'll talk about sort of as we come to the end. Is it a natural development progression? Because I assume you still have to continue development of Light Locker because you've got customers out there and you want to do stuff to that. And have you got like 2 development teams, one Light Locker and one for what's next?
Yes, and that's a good way to describe things at the moment. So yes, the developments with the integrated photonics, which is always going to be an integrated photonics. So think of the photonics and the digital stage as being tightly coupled together in what we build. The going forward, there'll be variants of the Lightlocker digital version, the initial versions, but this is all being designed so that the photonics can effectively be placed within that unit fairly seamlessly as the technologies develop. So actually, you may see variants coming up also with bringing the photonics in there with the FPGA devices. Eventually, the configuration of the how the photonics works with the digital within a chip package could extend outside the chip package as well into a even interfaces of how data is moved between chips. So a key area of development for us as well is thinking about how we can keep the advantages of the optics in as large a setting as possible within that entire digital circuit. That digital circuit can extend beyond chips as
So
well, which is
the clients who are buying your Light Locker now in its current digital configuration, will they be able to upgrade sort of seamlessly? What, even within the same box, you'll be able? Is it kind of whip out that
exactly,
and
yes.
well, that must
Yes, yes, that's how we're developing this. So
yeah.
think of the photonics as being the kind of elements within that system for generating those math functions, which now extend wider than the original Fourier transform based functions as well, and related to Fourier transforms are number theoretic transforms that form the bulk of the workflows in FHE and other PQC methods, but that now extends much wider as well. So we're now into modular arithmetic, we're now into polynomial-based workflows. So actually, FHE is one really important area,
Fully homomorphic encryption. Yep.
but it's one of several areas that we're working in now as well. So this is really a foundational technology that we are building.
So
That
have you got a
can
whole like
supply.
bunch of mathematicians in your team now, all working on these different? I mean, how big's your team today?
Absolutely, yeah. So we've got around 53 people right now. We have quite a unique blend of skills within the company. So we have obviously photonic engineers, optical computing experts. We have a full cryptography team as well, and
Oh,
mathematicians
right.
that work to optimize the algorithms to the photonic process. We have digital chip designers. We have analog chip designers. We have a full software team as well. So it's quite a unique blend of expertise that we have within Optalysys now. And I think I would say that some of our guys are really world leading experts in these algorithms now
Yeah.
that we
Now, of course, they all need feeding and watering, and indeed, what initially alerted me to Optalysys, because in truth, I hadn't heard of you until you announced earlier this year this very significant Series A extension funding round. I think it was in the order of £23 million, and when I checked back, it was an extension because I think you first raised funds a few years prior in July 2023, 21 million. So you seem to have some very supportive backers behind you. I assume there must have been funding pre-Series A. I mean, how did you get to, what was that, sort of grants or VC, traditional
yeah. So
seed
to
funding?
begin with, we had several seed rounds, so private investors at a small level. We also complemented that with grant funding. So we ran Innovate UK projects. We ran Horizon 2020 European projects, and also DARPA
Oh, really?
projects as well, US as well.
But if you
So
tell me about those, you have to kill me.
it was an interesting time, certainly, and DARPA as an institution is really interesting and really useful to us going forward as well. So we have technical projects in the future with them.
So how much would you say roughly speaking, you've raised to date then?
In total, we're well over 50 million
Wow.
GBP now. Now, to put that into context, though, the area of photonics and optical computing is actually super hot at the moment, and there's huge momentum in this. If you look to particularly the American-based companies that work on photonics technology particularly for interfacing and moving data between GPU-based systems in AI, for example, the level of funding going into them is an order of magnitude higher than what we can achieve really in the UK.
So are you going to have to look to the US then for future funding? Is that what you're suggesting?
Absolutely. So we are just opened our office on the West Coast. The US, Silicon Valley, thank you. And there's a big expansion underway on that as of now. The costs attached to producing the integrated photonics technology to its full extent into much larger numbers than we've raised previously.
What sort of ballpark would you say? I mean, just to give people a sense of how much developing this technology can really cost.
Absolutely, it seems to be hundreds of millions of dollars to produce the technology.
Okay, not pin money for sure. But
no, and the possibility is there to do this now, and it's fantastic because there is such momentum within this space now. Where I think previously we were almost running the kind of optical computing scene, shouting loudly, but I think the world has really woken up to the fact that photonics and optical computing is really the next.
Yeah, in fact, I've done podcasts with a whole heap of entrepreneurs and founders who are working in that area in some respect or other. But if in order to get to, you said the 2 or 3 years time when you've actually got the photonic chip, do you need significant further funding to get to that point?
Yes, absolutely. We are starting our Series B round as of now. The next amount we'll be looking for is 100 million plus. We're looking at the fine details of that at the moment. And if you consider the optical or photonic layer that we are building within a kind of 3D stacked chip, that is tightly coupling to the digital elements. Those digital elements need to be of sufficient performance to allow us to preserve the optical advantage that we have within the generation of those maths functions. So we are bringing together cutting edge technologies, both in the digital and optical realms here. And the things like advanced packaging is a key part of what's needed next as well. The really great thing is there's such momentum in this space now and precedence for doing this. What we have right now is the photonic chips as single function points. We have multiple tape-out generations behind us. In fact, we've had them on the cloud for 18 months or so. So the optical functions on their own are quite mature. The actual designs that we have are now well established. We've taped out the multiple foundries on that. The next stage is one of scaling and producing a high-density layer of those photonic functions that allow them to effectively speak to each other at extreme speeds and throughputs.
Well, as you look for the B round and beyond, are you starting to get any, I was going to say pressure, encouragement from US VCs to say, Nick, come on over here, the water's lovely, and just take your business to the US?
Yes, of course, and I'm certainly spending a lot of time in the US. Certainly through this year and next, setting that up. We have to have that US base next, undoubtedly. It's obviously the focal point for the world's tech development still. But the ties to the UK absolutely will remain. We are a UK business at the end of the day, and we fly the flag for UK tech development. We also have a key strategic partner with the UK government as well, developing in this space. So it's the next few months there'll be a balance between the build up in the US and continued build up in the UK and Europe as well. So we have two main sites in the UK already. So
And where were those, by the way?
Headquartered in Leeds, so where I am now, and also in Bristol in the southwest. We also have remote workers dotted around as well, as far away as India, Sweden, France, Ireland.
So while it sounds like the majority of future funding will come from the US, you feel very much that Optalysys will remain a UK-headquartered company, and this is where the IP is being developed, and as you say, key clients like the government will be here, because there'll be a podcast I'll be publishing in a week or so's time. There's an entrepreneurial founder who believes you cannot scale up a UK semiconductor, UK chip company here. You cannot scale up in the UK. You have to go to the US, and that frightens me. But I'm encouraged by what you're saying, because I'm interpreting that saying is that, as far as you're concerned, Optalysys will remain a UK headquartered company, irrespective of where the funding comes from.
Yeah, I mean, there's going to be a mix. I mean, there's obviously going to be the build up of the team in the US,
Yeah, sure.
and tapping a system out there. In terms of IP generation and so on, obviously there'll be a mix as well as the team grows. We've flown the flag for the UK for many years, and we still have ambition in doing that, of course. Equally, the tapping into the larger investment opportunities over there, we have to do next in terms of that kind of order of magnitude of funding, which is what it takes. Is needed. We have extremely good backers already on the deep tech investors, and obviously the round this time led by Northern Gritstone, which is doing fantastic work. The north of England startup in IMEC Expand, linked to IMEC across Europe and the US, but particularly centered on Europe for technology development, with a particular strong interest in photonics, and then Lingotto as well, and the part of the Italian Agnelli family office that.
Oh wow! Okay. Yep. And you may get a free car with every investment. You wish. That is really encouraging. I mean, do you, and particularly your investors, see a future on a listed stock exchange?
Absolutely, yeah. The ambition has always been that we grow the company and scale into something really significant on a global scale for this. And the path ahead of us is always challenging, but we are in such a good position in terms of accelerating next generation workflows. So we've talked about FAT, but there's a range of different workflows in both secure computing and AI contexts as well, in terms of large language models and Gen AI. There's opportunities everywhere right now, and as you'd be well aware of, in terms of the environmental considerations and the power considerations,
especially
how to continue to scale data centers with conventional technology is unsustainable. So the clamour for new types of technology, photonics being absolutely top of the list, with that is absolutely there now, and we're right in the middle of that development, offering something very different that the rest of the world does not have. So the success story as a UK company, hopefully we're building that out, and we'll see the fruits of that very soon. But this is the key area of development within computing now, which is effectively how you get more bang for buck out.
Absolutely. Well, I hope when the time comes that you do listen on stock exchange, you won't forget we do have one here in the UK, which is looking for brilliant companies just like yours. And I wish you very, very good luck on the journey. Nick New, co-founder, CEO of Optalysys, thank you so much for joining me on the BritChips podcast.
Thank you very much.